So as we get to this next page, you might want to pause the video and read over this section carefully. We're not going to spend too much time on it in the video, but I do want to mention just a little bit about each of these. So in this class, we'll be using the relative frequency interpretation of probability. What that means is that if I talk about the probability of an event, then what I'm really talking about is the fraction of the total number of events that correspond to, or sorry, I should say maybe the total number of outcomes that correspond to the event that I'm interested in. So for example, let's say that I'm rolling a die a bunch of different times. So if I roll a die a bunch of different times, I might get the results 1, 5, 3, 5, 2, 1, 6, 4, 1, and so on. Right, so I could make a gigantic list of these. And whenever I say something like the probability of getting a 1 is 1/6 with a die, what I really mean is that if you were to conduct this experiment over and over and over like I have here, then the proportion of these outcomes that would correspond to my event is 1/6. So in other words, in the long run, you would expect to roll a 1 about 1/6 of the time. So that's called the relative frequency interpretation of probability. There are some other interpretations of probability, but we're not really going to worry about them. This will be useful in practice. It just means that anytime you have a probability, that's the proportion of total occurrences that you would expect to correspond to your event in terms of this overall experiment, if your experiment were repeated a bunch of different times. Okay, so that's just the interpretation that we're going to use. That's not going to affect our actual computations. This is just how we're sort of fitting our understanding of probability to the models that we're using. So next, let's look at some basic set operations with probability. So we've already used some set notation today. This is just to describe particular events and the total sample space, which is just the set of all possible events. So remember that an event is a subset of your sample space. So if I'm talking about flipping a coin, then I would be maybe talking about the event that I flip a heads, which would just be the set that contains H. And that would be a subset of the total sample space, which is the set H, T. So we will always have that the probability of the sample space itself is 1 because something in the sample space is guaranteed. So the sample space is itself an event. It's just the full set of outcomes. There's also a way to express the empty event, and that would be using the empty set notation. And we're always going to have that the probability of an empty set is equal to 0. That just means that one of the outcomes in your sample space has to occur, assuming that you've designed everything correctly. So you can't have the probability of nothing happening equal something non-zero. The probability that nothing happens, or in other words, the probability of the empty event has to be 0. But we also have some set operations that we've talked about previously in the class, but that I want to review. So these will allow us to combine events. So we have a few of these. I'm going to define 3 of them. So there's the union, the intersection, and the complement, and those are going to be denoted like that. Now the union is what you get whenever you combine E with F. So we've used this notation before whenever we're talking about joining intervals together. So we would maybe have the interval from -infinity to 0 combined with the interval from 1 to infinity. That would be a way of describing this set, the set that goes from 0 off to the left and then from 1 off to the right. So here I'm taking the union of these 2 intervals, and when I combine them, I'm just putting that collection of outcomes or that collection of elements together. So that's what the union does. There's also the intersection. The intersection is just listing all of the elements that E and F have in common. And we can do this for intervals as well. So if I maybe take the interval from -infinity to 1 and I intersect it with the interval from 0 to 2, then what I'm looking for is the set of elements that these 2 intervals have in common. And if you need to do an interval intersection like this, you can always just sketch the two intervals. So this is the first interval, and this is the second interval. And then you can see what they have in common. In this case, it looks like what they have in common is just the set of elements between 0 and 1. So the intersection in this case would just be the interval from 0 to 1. But this intersection makes sense for any two sets. It's just asking, what do these two sets have in common? Or in our case, what do these two events have in common? And the complement will be everything outside of your event. So for example, the complement of flipping a heads would be flipping a tails. It's just everything that is not in the event that you were discussing. And you can see a typed up example down here at the bottom. I'm just going to move on to working through an example with you. But if you want to pause the video and read over that example at the bottom, you can. So here we're supposing that we're rolling a fair die. E is the event that we roll an even number. So E will be even number. And F is the event that we roll a multiple of 3. So first, I'm just going to describe the event E. So if I say find the event E, all that I mean is write it in set notation. So we want to write down E. E is the event that we roll an even number with a fair die, so the outcomes that we're happy with would be a 2, a 4, and a 6. Similarly, if we want to write the event F, F is the event that we roll a multiple of 3. The multiples of 3 between 1 and 6 are just 3 and 6. So there's E and F. Now, if I want E union F, that's what we get whenever we combine E together with F. So that would be 2, 4, 6, union 3, 6. So I'm just going to put these together. And whenever you write things in terms of set notation, it's technically okay to list the same element multiple times or to list the elements out of order. So set notation doesn't care about repeats, and it doesn't care about ordering for your elements. This would still describe the same set as 2, 3, 4, 6. Ordinarily, I'm just going to write this in the simplified form, 2, 3, 4, 6. But it would technically be okay to just put everything together in this sort of lazy way, like this. But these are the same set. So, in other words, having 6 as an element of the set listed twice is the same thing as just listing it once. The only thing that a set cares about is whether an element is inside or not. So here, 6 is an element of both of these sets, so these sets are identical. And similarly for the intersection, we're looking for the things that these sets have in common. And I notice that the only element that they have in common is a 6. We would still write this as a set. So we would still put that 6 inside of these curly braces, even though there's just a single element inside. And then if we want the complement of E, the complement of E is the set of all outcomes that are not in E. So we're looking at the sample space, which was 1 through 6, and I'm taking all of the elements that are not in E, so that would give me 1, 3, and 5. So notice that you can compute the complement just by thinking about what elements are missing from E. So in this case, if I wanted to get the full sample space from E, I would look at what's missing from it, and what it's missing is 1, 3, 5. But you can also take complements in terms of the original definition of the event, which is that E is an even number, or really E is the event that we roll an even number. So the complement of that event should be the event that you roll an odd number. And that I could then describe in set notation as I have done down here. So if it helps you to take the event in terms of just thinking about, or sorry, to take the complement in terms of just thinking about what the original event was, then that's totally fine. So if you want to just think that the complement of even is odd, or the complement of heads is tails, then that's fine. But you can also compute the complement by just thinking about what elements are missing from this original event in terms of your total sample space. Okay, and actually, just so that these all look the same, I'm going to box our answers here. So next, what we're going to talk about is the addition rule for probability, where we're going to put this set combination stuff to use. So what this says is that if you want the probability that E or F occurs, so you can read this as E or F, because remember, this is the set of elements that are in E combined with the set of elements that are in F. So this would be anything that's in E or F or both. So the probability that E or F occurs is going to be the probability of E plus the probability of F minus the probability of their intersection. So let me try to demonstrate why why this subtraction part is necessary in terms of just a picture. So let's say that you have two events E and F and they have a little bit of overlap. If I want the probability of E or F, that would be the probability of this set, sort of the figure 8 set, as a subset of my total sample space out here, S. So that would be the amount of area that's contained in this figure 8 divided by the total area of S, if you wanted to think of it in terms of that proportionality. But if we just took the probability of E plus the probability of F, that would be adding this area plus this area, but we've unfortunately double counted the area in the middle here, the area that they share. So if you just add together the probability of E plus the probability of F, you might be double counting anything that they have in common. And we'll see some examples of that in a second. But the reason that this term is showing up where you subtract what they have in common, or really the probability of what they have in common, the reason that that term shows up is just so that we avoid this double counting problem. So if E and F have some set of outcomes in common, then we don't want to double count them whenever we add E and F's probabilities together. So instead we need to subtract off what they have in common so that that middle term is only counted once. Okay, so that's what's going on in terms of a picture, but we'll see some hands-on examples in a second so that I can show you what we mean with some sets. However, if E and F have nothing in common, so if E lives over here and F lives over here, and those are disjoint events, in other words, they have no elements in common, then you can do the naive thing where you just add the probability of E plus the probability of F. That's because the probability of their intersection would be 0 because it's empty. So these formulas are consistent with each other. It's just that this last term would be 0 if we were applying this formula to disjoint sets. Because if E and F are disjoint, then this would just be the empty set whose probability is 0. So you'll need to use this top formula in general, but the bottom formula applies if E and F are disjoint. So let's look at problem 10. So let's compute the probability of either drawing a jack or a red-suited ace. So here, just to be especially pedantic, I'm going to write down that E is the event that we draw a jack, and F is the event that we draw a red-suited ace. Now notice that these are disjoint events in that they don't have any outcomes in common. So the set of jacks would be the set of jacks of each suit, and there are 4 of those, but that set doesn't have anything in common with the red-suited aces, which would be the ace of hearts and the ace of diamonds. So because these sets don't have anything in common, we could apply either of these formulas, but this top one will just have its third term equal to 0. That's just because E and F are disjoint, so E intersect F is the empty set. So I'm just going to use the disjoint formula here. We get that the probability that E or F occurs is equal to the probability of E plus the probability of F. The probability of E is going to be the number of outcomes in E divided by the total number of outcomes, and the same is true of F. There are 4 jacks, and there are 2 red-suited aces. So I would get this, and this is an example where you wouldn't actually want to be simplifying these expressions, because we do want to be able to add these together into a single fraction. And for that, it's beneficial to have the denominators match. So because these denominators match, I can just add together the numerators, and I would get 6 out of 52. And I would be happy with an answer like that. We don't really have to worry about simplifying things like this. Okay, in our next video, we'll talk about some more applications of this addition rule.